at this convertible codes framework, and we had looked at this formal definition for convertible codes, right? So Ni, Ki, Nf, Kf convertible codes had 3 components, if you recall. So we had a pair of codes, Ci and Cf, pair of partition functions, Pi and Pf, and conversion procedure T, which takes initial code words under Ci to final code words under Cf, right? So basically, our interest is in the cost of this conversion procedure, and the cost of conversion is basically cost of this conversion procedure T, right? So our goal is to design such as to minimize the cost of conversion, and we have 3 degrees of freedom to design. One is designing the codes, designing the partition functions, and designing the conversion procedure. Right, and we want to design this for given parameters Ni, Ki, and Nf, Kf, subject to some decodability constraints or requirements on both Ci and Cf. Because we have data encoded under both Ci and Cf at some point in time in the storage system, right? So at those points in time, the decodability constraints need to be met. For example, this decodability constraint could be the MDS property that we have looked at. That is, we need to be able to decode from any k out of the n blocks. That is, tolerating any n minus k erasures. And there are various cost metrics to optimize for, and as we saw earlier, right, and there is this axis, which is basically the degree, that is the number of nodes you need to access to do this conversion, bandwidth, network bandwidth, and disk I/O bandwidth, and also the computation CPU, that is the CPU cost. Right, so in this tutorial, as the first step in our exploration, in fact, what we have considered is both initial and final codes being linear and MDS. So we want both Ci and Cf to be linear and MDS. And the cost metric that we are focused on is access cost, which is basically the number of code symbols that you access in order to do the conversion procedure. Right, so both initial codes and final codes being linear is a good assumption. As I mentioned, most storage codes are linear. And MDS was just a good starting point because of the properties of optimal usage of storage space. And starting point again for the cost metrics was access cost. So just as a quick check, how many of you were present in my talk at TIFR? Just to know how quickly I can go over this. Okay, good fraction, but good fraction not present. Okay, so I'll make sure that the content is still comprehensible and followable. But at times, I might go a little bit faster, but you'll have access to the slides, so you can come back and look at it. Okay, so for access cost, each symbol that is read from the initial code word requires a read, so it's an access. And each symbol in the final code word, which is to be written, will be an access because it has to be written, right? So both read and write requests cost access. So access cost is the sum of these two quantities. One is the number of symbols read from the initial code words and the number of symbols written in the final code word. So first, I'll talk about a particular regime of parameters which we call the merge regime, and then I'll go into the other set of parameters and show how we can cover all the parameter regimes. Okay, so merge regime. So merge regime is the regime where you go from multiple initial code words into one final code word. That is, we have kf equal to lambda times ki, where lambda is an integer greater than or equal to 2. And lambda captures the number of initial code words combined to create one final code word. Basically, the picture would look like this, right? So you have lambda code words, initial code words, and all of them are converted into like one final code word. So kf is lambda times ki. Right? Ni and nf can be arbitrary. So this is the merge regime. So now let's look at lower bounds on the access cost of conversion for the merge regime. So let R be defined as n minus k, Ri for the initial code and Rf for the final code. Okay? So an intuitive way of remembering what R corresponds to is to think of the code as systematic, in which case r equal to n minus k would be the number of parities, right? Because k is the number of data blocks and n is the total number of blocks. Okay, so here is the main result on the lower bound on the access cost for the merged regime. So for all linear MDS convertible codes in the merged regime, the access cost is as shown. So if RF is less than or equal to RI, and if RF is less than KI, then the cost, the access cost is as shown here, which is sum of two quantities. The first term is basically the read cost. So recall that we are combining or merging lambda initial code words. So this lambda RF is basically reading RF symbols from each of those initial code words. Okay? And RF, it turns out to be the write cost, which is basically RF symbols or new symbols that are written in the final code word. And in the other cases, the access cost lower bound is as shown here, where again lambda ki is the read cost and RF is the write cost. And as you can observe here, ki is actually the number of symbols read in the default approach, right? So if you read all the message symbols from the initial code words, which is ki, then the cost would be this, lambda ki read cost, and then data blocks, think of it in a systematic code. So then data blocks are as is, you're not writing them. So the only RF new blocks would be written, and this would be the cost for the default approach. So basically, it's only in the first case we can do better than the default approach. So this lower bound is saying that in the second case, we cannot do better than the default approach. Okay, so the cost in the second case is same as in the default case. Okay, so now very quickly, proof sketch. So we'll introduce two new notation. One is we'll call symbols as unchanged if they remain as is as in the initial code word to the final code word. For example, data blocks, if the code is systematic and we retain the data blocks, there is no reason not to retain the data blocks. So those will be the unchanged symbols, right? So they will remain as is. And new symbols are the symbols that are not present in the initial code words, but are there in the final code word. So for example, if the code is systematic and we retain all the data blocks, then the parity symbols would be new, and those would be the new symbols. Okay, so the proof involves 4 key steps. So I'll go through them very quickly. So the first one is on equivalence of partitions. This is one thing to keep in mind, is only for the merged regime. So for the merged regime, it turns out that partition functions don't matter because we are combining all the initial code words into a single final code word. So basically, so we don't have to specify it. Okay? But it turns out partitions matter when we go into the other regimes, especially when we look at general regimes, it would be dependent on the partition functions. Okay, so the second step is we provide an upper bound on the maximum number of unchanged symbols. That is the number of symbols that can remain unchanged from the initial code words to the final code words. And here is the main result. So in any linear MDS convertible code in the merged regime, we can have at most ki unchanged symbols from each of the initial code words. Okay, so this follows from the MDS property. So if we have more than ki symbols unchanged, then from a single code word, then they would be dependent, right? So when you're getting more than ki symbols from a particular initial code word, within a code word, only ki can be linearly independent because the total number of message symbols is ki. So at most, ki can be linearly independent. So if we get more, then they'll be linearly independent, and hence the final code word will not be MDS. Okay, so we call convertible codes as stable if they meet this bound. That is, they have maximum number of unchanged symbols, which is basically ki from each of the initial code words, which is lambda ki. So if they have lambda ki unchanged symbols, then we call them as stable convertible codes. And stable convertible codes have RF, that's exactly RF new symbols, because we have NF. If you recall, RF is NF minus KF, and they said that we exactly lambda Ki, sorry, KF, and in the merged regime, KF is lambda Ki, right? So this is NF minus lambda Ki, and exactly lambda Ki is unchanged, and hence NF minus lambda Ki is new, and hence exactly RF number of symbols are new. Okay, so now the third step, we focus completely on only stable codes and derive a lower bound on the access cost. And then we will relax this requirement. So in this step, so we will focus only on stable codes. So recall that in stable codes, exactly RF symbols are new, right, as we just saw. So in the access cost, if you recall, we had read cost and write cost. And the write cost was basically the number of new symbols. And we already know the number of new symbols in stable convertible codes here, which is RF. So the only thing that is left to be specified is the number of symbols read. Okay, so here is the result. So in any linear MDS stable convertible code in the merged regime, basically the setting that we are considering in this part, one must read min of Ki and RF symbols from each of the initial code words. Okay? And if RF is greater than Ri, then one has to read Ki symbols from each of the initial code words. So let's focus on this first term, the cost in the first bullet, so which is min of Ki and RF. So recall that in the default approach, the number of read symbols is Ki, right? So in order to be able to do better than default approach, in this min, we need to be able to get RF, right? So for this, we need RF to be less than Ki. If RF is not less than Ki, the min would be Ki, which is same as default, so we cannot do better than default. And similarly, the second approach, the second case is anyway reading Ki from each of the initial code words, where we cannot do better than default. Yeah. Yeah. In the second case. No, in the first case, you need to access only min of Ki and RF. If you need to access Ki, then you cannot do anything better than default, right? So if you access all Ki, then it's same as default approach, right? RF. So you need at least lambda times RF. That's what this result is saying, right? So I will later on show you an example of a construction which can do that. I guess the question is, how is it possible without reading the KIs, right? So one thing that you can quickly go back to is the almost like a toy example that we saw earlier with the single parity check codes, where we were able to generate that additional parity by accessing only the parities of the initial code words, right? So basically, a similar thing will go on. We can generate the new parities for the final code word by using the parities of the initial code words. So you don't have to access the data message blocks. Yes, yeah. But we need only RF, right? So you don't need to read all RI. We have to generate RF symbols, RF parity symbols. It is sufficient to just read RF from each. You don't need to read all RI. Yeah, that's a good question, but you don't need to read all RI.
But to create the systematic part of the final code word, for that also you're saying you don't need to...
The systematic part is already there, right? So the data blocks which are there, they remain as is.
So that doesn't contribute to the, when you say read cost, this is only...
If you read those data blocks, it will cost to the read cost. But to generate the new parities, you don't have to read, right? So if you again go back to that single parity check example, we did not read the data blocks. So we don't have to, so the main reason is that as disks go through these transitions of failure rates, we are changing the code rate. And the data blocks will remain as is. We don't have to touch them unless we need to read them to generate the new parities. Yeah. Any other question? Okay, cool. So basically we need RF less than or equal to RI in order to be able to do better than the default approach. And similarly for the first case says that it needs to be, RF needs to be less than Ki. And these are the two constraints that you saw in the theorem, which I'll show again later. Okay, so RF less than or equal to Ri. Now in the fourth step, basically we get away with this restriction of stable convertible codes. So recall the step 3 bound was only for stable convertible codes. And next we show that any access optimal convertible code in the regime that we are looking at has to be stable. That is, if it is not stable, then it necessarily results in higher access cost. So it is okay to restrict only to stable convertible codes. So putting all this together, we get back this result that we saw earlier, right? And it turns out this bound is achievable. And this is what I'll cover next, achievability by providing an explicit code construction. And this will also answer some of the questions that we had, hopefully in a more detailed way. Okay, so the, yeah. Yeah.
That kind of corresponds to the number of failures
Yes.
that I expect to see.
Yes. It's n minus k, yeah.
So RF being less than equal to Ri is like I'm moving to a regime where there are going to be fewer, where I
Yes.
expect fewer, so it's like at
Right.
infancy.
Yes, exactly. So you can think about it going from infancy to useful life period. Yes. Okay, so the achievability construction is going to be systematic code, and it is for all parameters in the merge regime. Currently, we are focusing on the merge regime, right? So case 1 is the simpler case where default is optimal, right? So where if RF is greater than Ri, or if RF is greater than or equal to Ki, then we cannot do better than default. The case 2 is the more interesting one, where RF is less than or equal to Ri and Ki. So in this case, so I mentioned that the code is systematic. And in general, when we are looking at linear codes, one can specify a linear code completely by specifying what is called a generator matrix. Okay? So basically, since in a linear code, parities are just linear combinations of message symbols, you can specify it by specifying a generator matrix. And that generator matrix is denoted by G. Okay? And given any message vector M, you can multiply this message vector M with G to generate the code word. Okay, so that is how one actually encodes linear codes, and that's one of the reasons why linear codes are preferred, is because encoding and decoding are very easy, like matrix operations. So for systematic codes, G takes this form, which is I and a matrix P. So in systematic, we have message symbols, right? So that's why you have an identity matrix, because message symbols carry over. And there is this parity matrix, which basically will lead to n minus k parity symbols. And that's the parity part of the matrix. So since the code construction is systematic, we will have generator matrix for both initial code and the final code in this form, I and P. And the dimensions would be as dependent on the value of n and k. Okay, so what I'll do first is present some structural properties that this parity part of the generator matrix needs to satisfy in order to be optimal, and then give a construction and show that it actually meets those properties. Okay, then we will be done, because then we will know it is optimal. So the first one is actually a well-known result, which is encoding theory, which basically says that any code, MDS code with a generator matrix G of that form, is MDS if and only if that parity part of the generator matrix P is what is called superregular, which means that every submatrix of P is full rank. Or, so basically, every submatrix of P is non-singular. Okay, so we need Pi and Pf to be super regular, or every submatrix non-singular. Okay, the second property is what we call T-column block constructible. So basically, I'll first define what T-column constructible is, and using this build T-column block constructible. So we call a matrix M1 is T-column constructible by matrix M2 if basically we can use some subset of the columns of M2 to span M1. So suppose I have M1 and M2. If I can find some subset T, they need not be consecutive, that can span the columns of M1, then we say M1 is T-column constructible from M2. And then using this, now we will say T-column block constructible when we consider M1 now to be a taller matrix and M2 is short, and we'll call M1 to be block constructible from M2 if every submatrix which is formed this row-wise of the same height as M2 is T-column constructible. So basically, using columns of M2, we can span each of those subblocks. Okay, so now what is the connection between code conversion and T-column block constructibility? So recall that for access optimal convertible codes in the regime that we are looking at, we want to read RF symbols from each of these initial code words, right? Because read cost was lambda RF. That is, if we read RF from each of the initial code words, and if we can do conversion, then we will be optimal, right? So what this means is that a sufficient property is to have this matrix P of the final code to be RF column block constructible from Pi, which is the parity part of the initial code, right? So if this is met, then we can access RF symbols from each of the initial code words and then span, which is basically generate the PF, the parity part of the generator matrix, which means we can construct the parities in the final code word. Right? Okay, so now basically we need two properties, super regularity and T-column block constructibility. Okay, so here is the construction. So consider a field. So as I mentioned earlier, fields can be of size power of prime, right? So here just consider 2 to the d. And this is a common technique in achievability results where you will consider a very large field size because that helps in satisfying certain properties, especially the kind that I mentioned about super regularity. You want every submatrix to be full rank. That's harder when you're restricting it to a smaller field size. And then there are standard ways one could use to enforce that constraint, that you want every something to be full rank, right? So that is the reason why we will assume a large field size. Yeah. But the final thing that you recover is also high. So if you look at the ratio, the cost, that would still be less, right? By the way, so I will soon present a low field size construction as well. So these, as I mentioned, are basically what are called achievability results, where you are not looking for practical constructions, where the nature of the questions are like whether that lower bound is achievable or not, right? So we saw some lower bound. It is possible that it's not achievable at all. So the main advantage or the main purpose that achievability results serve is to show that it's possible to meet that. And then typically what one goes after is to construct low field size constructions, because if you don't know if it is achievable or not, then it might be futile trying to construct low field size constructions. Yeah. Yes, yes. So almost all, I don't know any of non-linear codes used in storage systems. It's all linear. So in fact, our results, I stated in the in the context of the theorems were all linear, but we believe that, from what we see in the proof, the linearity is not, and typically it happens in many other results, but not all, that linearity is not the main bottleneck. The MDS constraint is the main bottleneck in those bonds. So I think we have not worked it out completely, but the same things will hold true if the code is not linear too, but if we keep the MDS constraint. Okay, so we will have this field 2 to the d, which will be made large very soon. Let theta be a primitive element of the field. So again, this is something that I haven't introduced, but theta is called a primitive element if theta is such that if you take powers of theta, it will go through all the values in the field. That is, it will not repeat until it covers everything. So basically the power of theta for which you get back the value of 1, which is called multiplicative identity, is the size of the field. So you don't need the technical details of this. You can go back and look at it if you're interested. But just keep in mind that you keep taking powers of theta, you keep getting distinct values from the field. So that's like a primitive element. So now, here is the structure of Pi and Pf. Both of them have the same structure, where the ijth element is theta to the power I minus 1 times j minus 1. Okay, so I'll just actually take a more concrete example to show why this works. So suppose we are going from a 6-3 code to a 9-6 code. So both of initial and the final codes here have r equal to 3. Okay, so in this case, the construction will specify that Pi is of this form and Pf is of this form. So now here, let's see how the conversion happens and why this works. So the 2 rows are the 2 initial code words, and empty blocks are data blocks, shaded blocks are parity blocks. So data blocks will be retained as is. Note that it's not even being read for generating the parities, so they will not add any read cost or write cost. So now the new parities, which are these striped blocks, are generated by carefully designing the linear combination coefficients when combining the parities from the first initial code word, which is on the top, with the parities of the second initial code word, which is at the bottom. And the linear combination coefficients are some powers of theta. Right? So basically, like you can go through the details of why it works. It's available in the paper. So the above construction yields access optimal convertible codes, linear MDS, for all regimes under this merged regime, for all parameters. So at a very high level, by design of these Pi and Pf matrices, this block constructability property holds, because we can have those columns of theta and then some multiples of powers of theta to span the columns of Pf. And for super regularity, basically, as I mentioned earlier, this large field size can be used, and that constraint can be imposed. That's a standard way of making some matrix super regular. So that can be done. Okay, so now this shows achievability. So achievability results are basically, there exists, for some large field size, there exist cores which meet it, right? So now given this, as I mentioned, this is really large field size, and it becomes very large very soon in terms of the parameter value, so it's not practical. So we looked at low field size construction. So now, given that we know this bound is achievable, now this is an interesting exercise to see if we can construct low field size codes. So the key idea here is to pick the matrices Pi and Pf from a specially designed array which is of this form. Okay, so this array has, here one thing to note is the BIs need not be distinct. Given that, so this has this particular form where if you look at the left hand bottom corner to the right hand top corner diagonal, it's all identical. So the BIs are identical. Okay, so this form is called a Hankel form, and this turns out to be very useful in our construction. So let's take a concrete example again. Going from 9-5 code to a 12-10 code. So this time Ri is 4 and Rf is 2. Okay? And we will use a Hankel array of size nf minus 1, which is 11. So basically, the Hankel array looks like this, and we pick pi and pf as shown. So since Ri is 4, we need 4 columns for pi, and we pick it from 2 different locations of this array, shown in the pink shaded area. And Rf is 2, so we need 2 columns, and we pick it as the first 2 columns of this array. So now, kind of by design, PF is 2 column block constructible here, because first half is covered by the first 2 columns, and the second half is covered by the other 2 columns. They are identical, right? So spanning is by design trivial. Okay, and the field size here is just 11, which is nf minus 1. Okay, so this satisfies so far only the first one of the properties, right, which was like block constructible property. But the super regularity is still not guaranteed, for which we will impose additional constraint saying that we want to construct that array such that it is super regular, that any submatrix is super regular. So if we can do that, then our pi and pf will also be super regular. Okay? And it turns out that there exists algorithms which construct such arrays, which is this Hankel form, and they are super regular, and they were designed in the context of designing generator matrices for classical MDS codes, actually. Okay, so it turns out that these specific constructions turn out to be very useful to construct convertible codes. Okay, so these constructions actually yield a sequence of constructions which we parameterize by S, and it leads to a trade-off between the field size and the parameter range that we can handle. That is, so you recall that Ri was 4 and Rf was 2, right? But the theorem on the lower bound and achievability result held for all Rf up till Ri, but not that particular low field size construction. So if we want to cover more and more, take Rf more closer to Ri, the field size increases. And we don't know what is optimal in the sense that what is the minimum required field size for a particular parameter regime if we want low field size. Okay, so very quickly, I'll just mention that similar to merge regime, we consider another regime, which we call the split regime, which is the exact opposite, which is basically going from one final initial code word to multiple final code words. And again, we have bounds on the read cost and the write cost, and basically the access cost. So I'll not go into the details of it. I'll be sharing the slides. You can take a look at this. This part is actually a new result, so it's not present in our published ITCS paper, but we are writing it up and submitting. So, but this will be there in the slides. Okay, so read cost and write cost, and again, there are scenarios where you can do better than the default approach, and some scenarios where you cannot, right? So this else is the scenario where you cannot do better than the default approach. Okay. Upper bound, that is achievability, which is in the split regime, it turns out to be simple because actually you cannot do much better than default approach as much as in the merge regime. And basically, we can design a conversion procedure so that it is optimal for any MDS code. So in the interest of time, actually I'll skip this. It is achievable, the lower bound for split regime. I just want to mention general parameter regimes, that we can cover arbitrary parameter regimes using merge and split and their slight generalization. So they are like stepping stones to cover general parameter regimes. This is like one of the ways that typically you would try to do divide and conquer, right? So just thinking about general parameter regime right away was hard, but once you have these building blocks, then you can build up for the general parameter regimes. So here, partitions Pi and Pf turn out to be very important. So in fact, when we are going from this initial number of code words to final code words, so we have lower bounds on access cost. I'll not go through the details, but the key turns out to be the designing of these partition functions. So basically, given Pi and Pf, we can use merge and split to provide to cover any given parameter regime and some slight generalizations. But then what we do is optimize over these over these partition functions. So what should be the partition functions which will give the minimum cost? So we take this two-step process. Okay. Apologies for rushing through. So that's the key idea. So I'll skip this. So this is just showing how we use merge and split to cover a general parameter regime. Okay, so open problems in this realm of code conversion. I think this is an exciting new direction for coding for distributed storage applications. It has immediate significant potential for practical impact, just like how the reconstruction problem was. And so far, what we have looked at is the access cost, and that too for linear MDS codes, right? So one of the key directions to look at would be going beyond linear and MDS, and I would say beyond MDS because you do want to consider linear, so I would remove linear there. So going beyond MDS, right, like how in reducing reconstruction degree, we sacrificed MDS, but right, so by having local parities, right? So similarly, by sacrificing MDS here, how, what would be the bound, achievability, and constructions. And similarly, optimizing other resources, like for example, the network bandwidth, right? So then all the questions that has been asked and answered in the realm of optimizing for reconstruction bandwidth come up here, right? So in this, for the network bandwidth, and similarly, disk IO bandwidth will come in. As I mentioned earlier, disk IO bandwidth is only greater than or equal to network bandwidth. And similar questions have arisen in reconstruction problem as well. And one of the key questions here would be, can the disk IO bandwidth match the network bandwidth? So in the access cost, they are always equal. But in the bandwidth scenario, there will be differences, just like in the reconstruction problem. And similarly, CPU or computation wise, basically, there the main question would be, can these codes be sparse? So there have been some works in the reconstruction problem domain looking at sparse codes, because that would mean less computation cost when encoding and decoding. And so whether we can retain these other properties, but while still being sparse. Okay, so with that, I'll conclude the storage part. Any quick questions on this? If not, I'd like to quickly go through to the computation part, distributed computation part, which is also equally interesting and exciting. Okay, so then let's jump into it right away. Okay, so large-scale distributed computation is ubiquitous now, and the main reason there is to harness the compute, memory, and the network bandwidth and disk IO bandwidth of multiple servers together, right? So this is an economical way to achieve large-scale computation, and this has been the way for almost like a few decades now. Once this Google started this revolution mainly of building warehouse scale commodity equipment-based computing infrastructure. So there are many distributed computation frameworks now. Apache Hadoop, as I mentioned earlier. There's also what is called Apache Spark. There's also a newer type of distributed computation framework called serverless computing, each of them having different challenges, but the underlying principle is the same. And there are different kind of workloads, including machine learning, high performance computing, and so on, which are all done on distributed computation frameworks. And as we saw in storage, there are failures, unavailabilities, and stragglers here, and hence these all will affect tail latency, as we discussed in the storage realm. So basically, some of them will straggle or be unavailable, so some tasks will be slow. And again, like in storage, even for computation, there will be service level objectives to meet, and hence they need to rein in these tail latency, right? So another important reason why to rein in the tail latency is also that for many of the computation tasks, end users will be in the critical path, in the sense that these computations, for example, nowadays machine learning computations fall into the critical path. Almost every task that we do hits some or the other machine learning task. Right? So kind of these are all done in an online fashion, unlike some of the batch computations in other workloads. So like in storage, redundancy is one approach for adding resilience, but we need to add it in a resource efficient way because it comes at a cost, right? And now, again in this tutorial, our focus will be to look at coding theoretic tools or coding theoretic way of doing this, or in other words, this domain is called coded computation. Okay, so first here is the outline for this part of coded computation. I'll give a very high level overview of different models for coded computation. So people have looked at different tasks such as matrix vector multiplication, matrix multiplication, and also function computation, general across different inputs. Oh, wait a minute. Yeah, okay, so apologies for this. I should have had a slide without the highlighting, and I hope you can read the gray parts. And then I'll provide a unified view. So we have been, so then I'll focus on the third one, which is function computation on the inputs. And there we will look at specifically how one can solve this if f is a polynomial. So specifically there's a very nice work that provides a scheme called Lagrange coded computing. And then I'll talk about a unified view which provides a unified view of all these different approaches based on what is called a locality of code words. This is a recent work that we had. And then end with looking at coded computation for neural networks, like for example if you have machine learning inference. Okay, so there are several models for coded computation depending on different computation frameworks and tasks. And the common theme that you will notice is it's modular computation. Okay, so basically one task comprises of smaller tasks, and if you finish all those tasks, then you would have finished the goal of the computation. So some history. So in fact, this using coding to provide resilience to computation was studied many decades ago by Huang and Abraham and many other works that followed their work. And that domain is called algorithm-based fault tolerance, or it's referred to as ABFT. And it was primarily studied in the scientific computing or high-performance computing community. And more recently, and that was in the context of errors that can happen within a processor, like when you're doing computation, that can also happen. Like for example, if some gamma rays from the sun hits the CPU, and it does happen in some national labs and so on, and then when you're doing really high precision computing, even small bit errors matters. And there are errors that can happen in memory when the data is stored in memory during computation. And scientific computing community has cared a lot about this right from the beginning, because their simulations, etc., even small bit changes, even in LSB matters. But in the context of this modern distributed computation frameworks, coded computation was proposed by Lee et al. And this is where the term coded computation was proposed as well in this work. Okay, so for different models of coded computation, so the first one we'll look at is matrix vector multiplication. So you have a matrix A and a vector X, and A is typically large, and so we can divide it into sub-matrices A1 to AT, and typically it is distributed across servers, okay? So typically it is large. You should think about large to store in memory, right? Because when you're doing computation on it, you want it to be in memory, because otherwise if you have to access disk during computation, then it will be too slow, right? So that's the reason why one might want to distribute A across different machines. Let's say each of these sub-matrices have B rows. Then basically if one computes A1x to ATX, then we have the result of the computation, right? So this is the modularity you want to look for. What are the pieces that needs to be finished, right? So basically A1x to ATX. Okay, so now here A is of this dimension, the details does not matter. So what each worker can do is, given this vector x, it would have some matrix ai tilde, which is some function of these a1 to at, and it will output ai tilde x. So it will do a matrix vector computation on a matrix ai tilde, which need not be same as ai. In fact, it wouldn't be, like, because we want to encode it in some way, right? So basically, we have worker having x and giving out ai tilde x. Okay, so basically the entire scene would look like this. We have an encoder, and it will encode and give ai tildes to these workers. So this will, you can think of this like a pre-computation. So it would be done before. And ai tildes are some linear combination of ais. So in these slides, I apologize that they are a bit notation heavy. It might look complicated, but it is not. It's very simple. So it's just that in order to specify it completely, you need a lot of subscripts. But if you think about it intuitively, it's very simple. So basically, what this is saying is that each of these AJ tildes are linear combinations of AI, right? See, all these alphas are just linear combination coefficients. So you can ignore the subscripts just to understand what is happening. Okay, so now worker will do the linear combination of these. Worker I will do ai tilde x and send it to the decoder. So typically these encoder and decoder are at one machine. Okay, so this is like a master machine. So you have a master and you have workers. Master will spawn out the tasks and then collect back the results, and it will do the post-processing as well. So basically the decoder then decodes, and these coefficients for linear combination, that is the alphas, are chosen such that you can decode a1x to atx, right? So basically how you want to do is, any t worker outputs should help you to get back this. So similar to like how in storage, right? So now what you will have is some of them will be redundant, and that's where the resilience comes in. So it is okay if some of the worker output doesn't reach the master. So if, as long as t worker output reaches the master, then you can decode. Is that clear? Any questions on this? Okay, cool. So similarly, if the matrix is fat instead of being tall, then you can do chopping along columns, and very simple. And there has been a lot of work in this space. This has been a very active area recently. And again, I won't be able to cover all of them. Again, you can look at these references and their references and the works that cite them to get a feel of the whole area. Okay, the second one is matrix multiplication. So similar thing can be done, okay? So now we have two big matrices. Each of them could be split and stored on different servers. And then in order to do, let's say the submatrices are of size B, then in order to compute AB, basically you'd have all these smaller parts to be computed. Right? Again, this modularized theme. So it suffices to compute AIBJ for all of these, I going from 1 to T and J going from 1 to T, right? T squared terms. So the A and B need not exactly have same number of sublaws. It's just for simplicity of exposition here. It could be T and it could be some parameter M, right? So still the picture would remain same. So currently in this example, we have T squared smaller computation units to finish. And the scenario would look the same. So now each worker will do a matrix multiplication, smaller one, ai tilde, bi tilde, and it will send the output to the master, right? So the scenario would look like this. So you have this encoder. Encoder will send ai tilde, bi tildes, which are again, in notation might look scary, but it is very easy. It's just saying that it's linear combination. And alphas and betas and the subscripts are all just to depict that it's a linear combination, right? So here we are all talking about linear codes. That's why they are linear combinations. So basically now, given these linear combinations, You can think about if you want to, in general, any other function. So basically, given to each of these workers, and each worker outputs AI tilde times bi tilde, smaller submatrix multiplication, and decoder will decode. So recall that we need t squared of those smaller units, right? So basically now, the goal would be to design these coefficients, A, alphas, and betas, such that out of some W number of workers I have, if as long as t squared come back, we can decode each one of them. Right? So similar to as in storage. So there will be some redundancy. So the thing is, we won't know which one will straggle, which one will fail, but as long as any t squared come back, the decoder should be able to decode. Again, even on the matrix-matrix multiplication, there is a lot of work, and the same way, you can go and look at it, their references, and the works that cite them. Okay, so the last model that we'll talk about is computing a function f for different inputs. So we'll have k inputs x1 to xk, and we want to compute f of x1 to f of xk. Okay? And let's say we have W workers. So worker I can evaluate f at some evaluation point xi tilde. Right? So similarly, how in the previous models, the worker could do the miniature version of the original computation. So here, the modularity is basically coming from the k inputs. So we want to do f of xi for k different inputs. So basically, we have this W workers. Each of them would be given some xi tilde, which would be some encoded form of x1 to xk. And then each of the workers will output f of xi tilde, right? So this is when there are no stragglers or unavailabilities. And suppose we want to tolerate up to s arbitrary stragglers. So I'll keep referring to it as just stragglers. In general, it could be just fail to return as well. So in the interest of time, I'll just keep referring to them as stragglers. So in this case, again, workers would be given xi tildes, right, encoded form. It's just that some of them will not return the output because they are straggling. And now the decoder needs to use W minus S, because W is the total number of workers. So W minus S outputs to decode. Okay, so this is the framework that we will continue for the rest of this part on coded computation, right? Any questions on this? Yeah. Yes, it is. Yes. As we will see, some are very easy, some are hard, and some are open. Don't know how to handle. Yeah. Yes, yes. Good question. Yeah. So how it is encoded is dependent on function f. Some function f will be known beforehand. Yeah. Okay. So now let's delve a little bit deeper into it. So now for this, that was a very good lead question. So now let's say this function f is linear. Okay. So f is linear in the inputs, and we want to compute f. Well, up to s workers can straggle. So by linearity of f, as you all know, if f is linear and if the input is a linear combination of xi, then f and this linear combination will commute, right? So basically, f of this linear combination is equal to linear combination of these fi's. Right? So because of this, designing a coded computation scheme is almost trivial. It's very easy. So basically, we can have a code, like any MDS code that we have been looking at, right? So we can have that code as this xi tildes, and then the workers will just do their normal job, like f of those inputs, and then they will output f of xi tildes. But magically, because of linearity, what we will have at the output will be the same code, but on f of xi's, right? So we had encoded xi's using a code, but because of linearity, now at the output, it will be the same code on f of xi's, and which is nice, because now some of them will be missing, but we can decode, because if we had used an MDS code, for example, the outputs will form an MDS code, right? So thus, these alphas can be chosen to decode, but it could be an MDS code, for example, right? So linear functions are nice. easy, right? But most of the functions that you're interested in computing are not linear, right? So in these computation frameworks, for example. Okay, so now there's a very nice work which then looked at and specified how one could do the same for polynomials. Okay, so let's move on to polynomials. So we look at specifically multivariate polynomials, and it's a rich class because it encompasses linear functions, multilinear functions, matrix multiplication, and also like general tensor algebras which come in different applications. Encoded computation for arbitrary multivariate polynomials were considered in this seminal work by Yu et al. And the scheme that they specify is called Lagrange coded computing. And we will see very quickly what that is. So basically, we have this encoder. We have k inputs, just as a recall for the setup. Then encoder sends xi tildes to workers, and decoder gets f of xi tildes, and some of them will be missing, and the decoder has to decode. Right? And the resource requirement here, the key resource requirement that we will be looking at, is how many workers are needed in order to do this work, in the sense that I want to compute k evaluation points, f of xi's for k such xi's, how many workers are needed in order to tolerate up to s stragglers. Okay, so that's the resource requirement, smallest achievable W. Okay, so in this Yu et al. Work, they considered linear encoding. So the encoder takes xi's and the xi tildes are linear combinations. And similarly, linear decoding. So at the decoder, so this is a lot of symbols, but I'll explain at a very intuitive level, so you don't have to look at the symbols. So what this is saying is that basically you will have some subset of size S straggle, because we want to tolerate up to S stragglers. So some subset of size S of the outputs will be missing. And the decoder will take linear combination of whatever is available. So it takes linear combinations in order to get back the original function, which is f of xi's. Okay, so I'll take a simple illustrating example which will show what is happening. So basically, suppose we want to compute a polynomial f of x1, x2, which is just x1 times x2. Okay, so this is a multilinear polynomial, right? So and at inputs, let's say 3 inputs, minus 1, 1, 0, 1, and 1, 1, as shown here, and subject to S stragglers. So the first step is to consider a degree 2 polynomial. In this case, I'll take y squared, and I've written it like a point, y comma y squared. Okay. So what is the interesting property of this polynomial is that it intersects the given 3 points. Basically, it goes through the 3 inputs. So as the first step, what we want to do is find a polynomial that passes through the given input points. Okay. So after that, now consider this polynomial, which is f of r of y. Okay, so f of r of y, where r of y, now consider it as a point, y squared, is y cube. Okay, because f of x1, x2 was x1 times x2. So now for this, note that if we put a y as minus 1 and 0 and 1 respectively, we get back the value of f at the 3 points that we need. Okay, so basically now this f of r of y looks like this, and if evaluated at particular points, some specifically designed points, it will give back the f of xi's that is needed. And thus, if one recovers f of r of y, which is a univariate polynomial, then you can calculate it at specific locations, evaluate at specific locations, in this case at minus 1, 0, and 1, and get back what we wanted. Okay, so this is just a very simple example for this Lagrange coded computing scheme, which basically does the same thing but in general. So basically what this Lagrange coded computation scheme does is to define this new polynomial r of y, similar to as we did in the example, which goes through all the input points. Okay? So there is a way to construct such polynomials, and here this is the form, and this is, where did it go? I had an animation. Okay, so I do understand, because this is called Lagrange polynomial. So you might have learnt it in your math classes. So given k points, you can find a polynomial which goes through those k points. Okay, so that's called Lagrange polynomial, and that has this form. And basically, there will be some beta i's where that polynomial evaluated at beta I is equal to xi, okay, because it's going through those points, right? So consider now f of r of y, similar to what we did in the example. So then f of r of y evaluated at those beta i's again will give us f of xi, right? Because r of beta I is xi. Okay, so this is the key thing to remember. Okay, and another thing to remember, which will come handy later, is degree of this function f of r of y. So degree of this function f of r of y is what? So we are kind of composing two different polynomials, right? F is degree of f, and Lagrange polynomial for k points is of degree k minus 1. Okay, so that's a result, and you can think of it similar to what we saw earlier, right? So given k different points, we had said that there is only one polynomial that goes through it, and it's degree k minus 1, right? So in fact, one way to construct the polynomial is this Lagrange polynomial, Lagrange interpolation it is called. Okay, so now basically the first property of f of r of y says that if we can compute f of r of y, then we can obtain f of xi, right? So basically at the master, it can interpolate to find f of r of y, as we will see, and then evaluate it at beta I to get back f of xi. Okay, so goal. So now our goal is to recover f of r of y at the decoder by being tolerant to up to s stragglers. Okay, and then the master will evaluate f of r of y at beta i's. So now one natural question that might come to mind is, then the master can evaluate f itself at xi's, right? So what is different here? So the difference is f of r of y is a univariate polynomial, whereas xi's could be in a very high dimensional space. So that f of xi would be hard to compute, and that's why you are kind of sending it out to the workers. And then here the problem is converted into, finally what the master has to do is a simpler task. So basically these evaluations of this univariate polynomials is simpler, right? Okay, so now we want to recover f of r of y. Is that clear? So that is the goal. So now how can one do that? So the scheme is the following. So you take k minus 1 times degree of f, which was the degree of f of r of y, right? And you again use the result that we have seen earlier. So if we have a polynomial of degree k minus 1, then if you know its evaluations at k points, which is degree plus 1, then basically you can recover that polynomial, which was how we did Reed-Solomon decoding, right? So similarly here, we have a k minus 1 times degree of f degree polynomial. And if we have that plus 1 evaluations, we can recover. But we will add plus s more. Why? Straggler resistance, right? Because some s of them can straggle. But even if s straggle, we will still have sufficient, because we will have degree of that polynomial plus 1, and then we can recover, which is basically through interpolation. Okay, so basically each worker I computes f of r of beta I at these some distinct betas, and then some s of them might straggle, and then decoder uses whatever comes back to interpolate f of r of y, and then it evaluates at the specific beta i's to get back f of xi's. Okay, so it turns out that this scheme works when degree of f is less than or equal to s plus 1. So basically, what we know through this Lagrange coded computing scheme is that when degree of f is less than or equal to s plus 1, you can do with these many workers. Okay, so degree of f times k minus 1 plus s plus 1. And then if degree of f is greater than s plus 1, in fact, cannot do, so this scheme cannot do better than s plus 1 wise replication. So recall that if you want to be tolerant to s stragglers, you have to do s plus 1 times replication of each, because all s copies of a particular task can straggle. Right? So this part is same as replication. So for the same, the setting that we are considering, in fact, the Yu et al. Work provides a lower bound. So recall that this scheme was achievability in the sense that it provided a scheme to do it, right? But they also have a bound to show that this is needed. Okay, so this much is needed, and the Lagrange coded computing scheme achieves this bound. Okay, but this is for the setup of linear encoding and the setup that I described earlier. So now given this, I'll next move on to this unified view that is based on locality of code words, which we have been working on. And currently the paper is not yet available, but we will put it up on archive soon. It's under submission. Okay, so how do we do this? So what we do is we associate, yeah. 10 more minutes? Sure, yeah, okay. So then what I'll do is I'll quickly go through this, and I will leave out some parts which are details that you can look through, okay? So basically at a very high level, what we are doing is we define a code word for a function, okay? So given a function f, we define a code word as it's a vector of its evaluations at all points in the domain. Okay, so this is all abstract, so this is not something that the system computes. So this is all just a different way to look at the setup or the problem. Okay, so now in this, so recall that as we saw earlier, replication is needed sometimes, right? So in the typical notion of a code word, there is no replication within a code word. So in order to incorporate that, we consider what is called S repeated code word, which considers the same code word that I mentioned above, but repeats it S plus 1 times. So it's S plus 1 times repetition. As we just discussed, you need S plus 1 repetition to be S straggler. So in some cases, you might need replication, right? As we saw earlier, there were 2 cases. So to handle that, I will consider this specially designed code word for a function f. And then we talk about, so we define this new notion called computational locality of functions and a particular associated code word. Now for a code C, now we will say that C has computational locality L if for every set of K code symbols, there is a set of L symbols using which you can reconstruct those K symbols, just like what we are trying to do in this coded computation with S things straggling. That is, pictorially it's much easier to describe. So for every K symbols, here in this example showing first K, there is some set of L symbols using which you can recover these K symbols, out of which S can straggle. So any L minus S is sufficient. So then we will say that it has computational locality L. Okay, so what I'll do is, apologies for rushing through this. So I'll only mention the key points that, using which you should be able to follow through the slides. Okay, so we are saying that it has computational locality L, and it turns out that this computational locality L very nicely maps to the minimum number of workers needed. As you saw, there is a direct correspondence, right? So you can recover any K using L of them where S can straggle. So if the code word is like that, then you can reconstruct with this L number of workers, right? So basically this is done via what is called as a local correcting scheme. And basically, a local correcting scheme is, this is in general, so this is a well-studied area, local correction of codes, is basically given a code word, if a particular symbol of a code word is in error, then can you correct that error by accessing only a small fraction of the other code word symbols. Okay? So similar to the reconstruction degree problem that we saw earlier. Okay, so it turns out that if the function is a multivariate polynomial, then the associated code is what is called a Reed-Muller code. So it's a very well-studied, well-known class of codes. And there are several works which have looked at local correction schemes for Reed-Muller codes. So using that, basically what we can do is design a coded computation scheme for multivariate polynomials under this new viewpoint now, because we know that for polynomials, the associated code word is Reed-Muller code, and hence they have local correction properties. And because of that, the result that we saw earlier, that is k minus 1 times d plus s plus 1, naturally comes out as the locality, because if you go through the details, the degree of that, the Reed-Muller code locality comes out to be this. So if you look at the computational locality of the Reed-Muller code, it comes out to be this, and hence we will directly get a coded computation scheme. So I'll not go into very much into the details of this in the interest of time. What I want to move on to, this was perfectly the bad time for PowerPoint to do saving, but let's do it. Okay, so basically, I'll use this time. So basically, this new viewpoint helps us to recover, that is, re-derive these known results with this new viewpoint of looking at locality of code words. And also it has some other advantages. One is this unified view, so we can actually explain matrix vector, matrix matrix, and the polynomial schemes in this one unified way. And also, actually we can show that this s plus 1 wise replication, which was there in the existing works bound, is actually not fundamental. So we can do better than s plus 1 wise replication if one exploits locality of input symbols. So this locality based viewpoint helps us to exploit locality of the input symbols, and thus show that s plus 1 wise replication is not really fundamental, and one can design coded computation frameworks that overcome that. So in the interest of time, I will leave that and quickly rush through at a very high level coded computation for neural network inference, because I think it is a very interesting area, because neural networks are highly nonlinear functions. So currently in the coded computation theoretical side of things, there are no ways to handle it. Okay, so what I'll do is, I'm sure you all have heard the importance of, at least in the current times, neural networks and how they are being used in variety of applications. So there is a lot of interest in being able to handle neural networks, right? So I want to quickly jump through the motivation, because I'm sure it's well known and you can go through the slides. So currently, the main application here that we're looking at is what is called prediction serving systems. So prediction serving systems are systems that deploy already learned machine learning models, take in queries, and give out the predictions. So you can think of many of the machine learning services that companies have. Like for example, Microsoft, Google, each one of them actually have their own image classification services. So you send an image, they will classify it for you and give back the predictions. So that's like a prediction serving systems. So typically what these systems have is multiple copies of the same model, like think of a neural network running on different servers. Because the query rate is so high, one server cannot One server at Microsoft cannot respond to everybody's images, so it will be running on multiple servers. So you'll have something like this. So these instances are called model instances. They are running on different nodes, right? So basically they have a front end. So your queries come in, they are dispatched to different instances, and then results come back to the front end and then they go back. And then there are failures, and I'm skipping through this. Right, so and then just to make sure the language is clear, we have this function f running, which is the model, which can be a neural network. There are inputs and there are outputs. And some of the outputs might fail. And basically your interest is to encode the inputs in some way, pass it through a redundant computation, and such that the decoder, even if one of the f of xi is unavailable at the decoder, it can use this redundant path and decode. So it's the same model that we have been looking at, but how it is presented is different. So I just wanted to make sure that is clear. Okay, so now in the prediction serving systems, these F will be neural networks. Okay, and the key challenge is that neural networks is nonlinear, and for general nonlinear functions, we don't know how to handle it. So I leave it this a couple of slides just saying how we were able to handle it. So basically what we propose is a learning-based approach which combines machine learning and coding. So basically, we learn the various components of this coded computation framework. And what were those different components? There was this encoder, redundant computation unit, and the decoder, right? So we have two approaches at a very high level. There's no math here. So learning a code, so first one is basically we keep the redundant computation same as the original computation F, and we learn encoder and decoder using neural networks. Okay, so you can find more details in the paper. It actually works out pretty well. I won't have the time to show you the results. So we have results on the image classification and a variety of other tasks like speech and image segmentation. It works pretty well. Okay, and so this was learning the code, basically where we are learning encoder and the decoder. And I'll just show you the other approach. Yeah, so the second approach is actually, so the first approach of learning the encoder and the decoder has some downsides when we look at real world systems, because it increases the complexity of that front end, which has the encoder and the decoder. If now encoder and decoder are neural networks, now that front end needs to be bulky and so on. So instead, the second approach, we keep the encoder and decoder very simple, just like addition and subtraction, but learn a new neural network for this redundant computation unit. Okay, so using that, again, it does pretty well. The results are available in the paper. So this was at ACM SOSP last year. And basically, we call it as a parity model. So you had original models, and now we have parity models. So it's just like we had data and parity. Like here, it's like a parity computation. Okay, so it's like a new model, but it's a parity model. And we have different types, which is generic, or it can be task specific. I'll not have the time to go into that. And if you are interested in this space of coding meets machine learning, so I would encourage you to take a look at that. We have really good results on variety of tasks, all like popular state-of-the-art tasks, very different networks, including ResNets, which are like very popular, and different kinds of encoders and decoders. Okay. Apologies for rushing through again. What I'll do is just summarize and finish. Okay, so in conclusion, we are in this data-driven world, like large-scale computing and storage is ubiquitous, and they are foundational for this internet-driven services, which we see everywhere, right? And in this scale of operation, unavailabilities and failures are the norm, And there is a need to introduce redundancy in a resource efficient way. And hence, there is a role for coding theorists to play here to have a potential for real world impact, right? So I think there are exciting new problems in this space, some of them that I discussed, with the potential for real world impact. And I'll share the slides, and I've also discussed some interesting open problems in the coded computation domain as well. With that, I just want to mention that for the works that I covered from my research labs, so the publications are found, can be found on my webpage. And we also have code available for this machine learning work that I mentioned on our GitHub page. So it's written, well documented, so that it is easily usable. So if you're interested, I would encourage you to go and play with that. With that, thank you so much. I've held you much more than specified. Thank you for staying back, and I would be happy to take any more questions if you're interested. We can do it either here or offline, it's fine. Offline, yeah, sure.
That's time for
Thank you all. Yeah.